Sketch the graph of the function f of x equals x squared plus 3x divided by x minus 1 by determining the parts a through I. F of x equals x squared plus 3x divided by x minus 1. So it has a denominator. The numerator can be factored. There is a common factor of x. Factoring that out will leave behind x plus 3. The denominator does not factor at all, and it will remain as x minus 1. The domain requires that the denominator cannot equal to 0, so x minus 1 cannot equal to 0 here. We can solve for what x cannot be by adding 1 to both sides, and x cannot equal positive 1. So for part A, the domain will be all real numbers except positive 1. It will be all real numbers to the left of positive 1, negative infinity up to positive 1, not including it, round bracket, union, and all real numbers to the right of positive 1, not including it, round bracket, up to positive infinity. For part B, we want to determine if there's any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of, in the numerator, an even power of x, which will have y-axis or even symmetry, added with an odd power of x. This is an implied first power, which will have origin or odd symmetry. Since the two do not match and they are added together, f of x will have no symmetry. F of negative x will be negative x squared plus 3 times negative x divided by negative x minus 1. In the numerator, a negative squared is positive, x squared. A positive 3 times a negative x is a negative 3x. In the denominator, we can factor a negative out, which will leave behind a positive x and a positive 1. That negative in the denominator can move to the front of the entire expression. Comparing this result to the original, it definitely does not equal the original because it has a negative factor out in front of it, and some of the terms have the same sign and some of the terms have the opposite sign. So this does not equal f of x, and it will not have y-axis or even symmetry. Comparing the result to the original with the negative factored out, in the numerator, the first term has the same sign, whereas the second term has the opposite sign. And so f of negative x also does not equal negative f of x. And it will not have origin or odd symmetry either, so for symmetry it has none. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate of 0 back into the original function y equals f of 0, which will be 0 squared plus 3 times 0 over 0 minus 1. 0 squared is 0, 3 times 0 is 0, 0 minus 1 is negative 1, 0 plus 0 is 0 over a negative 1. 0 over any non-zero number equals to 0. We had an x-coordinate of 0, and we found a corresponding y-coordinate also of 0, so the origin is the y-intercept. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. We want to start by taking f of x, factoring both the numerator and denominator, and canceling any factors from the numerator and denominator. The numerator has no factors that match with the denominator. There are no factors that cancel. Y, which is f of x, can be set equal to 0, and we can set it equal to the remaining numerator after canceling out any factors. So we have x times x plus 3. We can solve for x because it's factored. We'll end up with x equals 0 from the x factor, and x equals negative 3 from the x plus 3 factor. We had a y-coordinate of 0. These are the corresponding x-coordinates, so we have 0, 0, and negative 3, 0 as the two x-intercepts. For part E, we want to determine the vertical asymptotes. This is done by taking the denominator that remains after canceling any factors from the numerator and denominator. No factors canceled. We had an x minus 1 left over in the denominator of f of x. Setting it equal to 0 and solving for x. X equals positive 1 will be the vertical asymptote here. We can determine the behavior on the left side by taking the limit as x approaches 1 from the left side of f of x squared plus 3x divided by x minus 1. Plugging in a positive 1 in the numerator, 1 squared is 1, plus 3 times 1, which is a 3, 1 plus 3 is a 4, divided by, plugging in 1 in the denominator, 1 minus 1 is a 0, but we're approaching 1 from the left side here, which means we're less positive than 1. If we subtract 1 from that, it will be a negative number, yet it is approaching 0. The numerator is a positive 4. Positive over negative is a negative. Non-zero over 0 is an infinity. We can also determine the behavior on the right side by taking the limit as x approaches 1 from the right side of f of x squared plus 3x over x minus 1. Plugging in a positive 1 in the numerator, 1 squared is 1, plus 3 times 1, which is a 3. 1 plus 3 will be a 4. Divided by 1 minus 1, which is a 0. We're approaching 1 from the right side here, which means we are more positive than 1. If we subtract 1 from that, it will be a positive number, though it does approach to 0, so it'll be a positive 0. We have a positive 4 in the numerator. Positive over positive is positive. Non-zero over 0 is an infinity. For part F, we want to determine if there are any holes in the graph. This will happen when f of x is fully factored and there are factors from the numerator that will fully cancel with the denominator. We had no factors that would cancel, so for holes there are none. For part G, we want to determine the end behavior, horizontal asymptotes or slant asymptotes. F of x has a highest power term in the numerator of x squared and a highest power term in the denominator of x to the implied first power. Since the numerator has a higher power than the denominator, f of x will not have any horizontal asymptotes. Since the power in the numerator is exactly 1 higher than the denominator, f of x will have a slant asymptote. The slant asymptote can be determined by dividing the x minus 1 denominator into the x squared plus 3x numerator. We need to multiply x by whatever is needed to make it match the first term, which is x squared. That will be an x. Since x times x will be x squared, we now multiply this x times this x minus 1, which will be x squared minus x, and we subtract that from the one above. X squared minus x squared cancel. A positive 3x minus a negative x minus a negative x is plus x. 3x plus x is 4x. We now need to multiply the first term x to make it match the 4x. That will be a positive 4. Multiplying the positive 4 times the x minus 1 will give 4x minus 4. We now will subtract this entire result. 4x minus 4x will be a 0. An implied 0 minus a negative 4 will be a positive 4. X cannot further divide into a 4 because it does not have an x, so 4 will be part of the remainder that is still being divided by the x minus 1. The slant asymptote is the linear function that remains after ignoring the denominator. The denominator goes to 0 as x approaches positive or negative infinity. So the linear function is x plus 4. That will be our slant asymptote. It will be y equals x plus 4. For part H, we want to determine The intervals of trend, relative maxima, relative minima, plateaus, and cliffs, all of this involves the first derivative, f prime of x. We'll take the first derivative from f of x. F of x, we want to use the non-factored version, is a quotient of two expressions of x, so a quotient rule will be needed here. This will take a little bit of room and can be worked out on another page. F of x is x squared plus 3x divided by x minus 1. The first derivative, f prime of x, will make use of the quotient rule, derivative of the numerator, which is a 2x plus 3, times the denominator left alone, x minus 1, minus the numerator left alone, x squared plus 3x, times the derivative of the denominator, which is a 1. And the entire thing will be divided by the denominator squared. In the numerator, we can FOIL out these two expressions. First, 2x times x is 2x squared. Outside, 2x times a negative 1 is a negative 2x. Inside, positive 3 times x is a positive 3x. And last, positive 3 times negative 1 is a negative 3. And we can distribute a negative and a 1 into this expression, which will give a negative x squared and then minus 3x. All of this is over x minus 1 squared. We can combine like terms together in the numerator. 2x squared and negative 1x squared will combine to be positive 1x squared. There is a negative 2x, a positive 3x, and a negative 3x. The positive 3x and the negative 3x will cancel. So that'll leave a negative 2x. And then there's a negative 3 that does not combine with anything, all over x minus 1 squared. We want to fully factor the first derivative. The numerator is a trinomial quadratic and can possibly trinomial factor. We need two numbers that multiply to be a negative 3 and add to be a negative 2. Negative 3 and positive 1 will take care of that. And all of this is over x minus 1 quantity squared. This is the version of the first derivative we're going to want. So it was x minus 3 times x plus 1, and then all over x minus 1 squared. We have the first derivative written as a single fraction. All powers are positive, and it is fully factored, so we can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, the x minus 3 factor gives x equals positive 3, and the x plus 1 factor gives x equals negative 1. From the denominator, the x minus 1 factor gives x equals positive 1. We will now check to see which of these are in the domain. The domain is all real numbers except positive 1. X equals positive 3 and x equals negative 1 are both real numbers, and they are not equal to positive 1, so they are both in the domain and they are both critical numbers. X equals positive 1 is not in the domain. We will cross it out. We can now draw a domain line, a line representing the domain. It has no left end because it begins at negative infinity, and no right end because it ends at positive infinity. It does not include positive 1 because x equals positive 1 was found to be a vertical asymptote. So we can indicate it as a vertical asymptote by a dashed line. We can now put all critical numbers on here in order. Negative 1 is to the left of positive 1, and positive 3 is to the right of positive 1. The domain is split into two intervals. This further splits it into what is now 4 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to negative 1, contains negative 10. The next interval, negative 1 to positive 1, contains 0. The next interval, positive 1 to positive 3, contains 2. And the next interval, positive 3 to positive infinity, contains positive 10. We can test the trend by plugging the test values into the first derivative. We only care whether it is positive or negative here, so the best place to plug in is the fully factored version. That is this one here. The denominator here is a factor raised to an even power, which will make it always be positive. And so the denominator will not affect whether the first derivative is positive or negative, so the only portion of the first derivative that matters is the numerator. Each of those factors can be positive or negative depending on the value of x. Plugging in the test value of negative 10, negative 10 minus 3 is negative, negative 10 plus 1 is negative, negative times negative is positive. We have a positive first derivative. This corresponds to an increasing trend. Plugging in the test value of 0 into the portion of the first derivative that matters, 0 minus 3 is negative, 0 plus 1 is positive, negative times positive is negative. We have a negative first derivative. This corresponds to a decreasing trend. Plugging in the test value of 2 to the portion of the first derivative that matters, 2 minus 3 is negative, 2 plus 1 is positive, negative times positive is negative. We have a negative first derivative. This corresponds to a decreasing trend. Plugging in positive 10 to the portion of the first derivative that matters, 10 minus 3 is positive, 10 plus 1 is positive, positive times positive is positive. We have a positive first derivative. This corresponds to an increasing trend. Right at the critical number of x equals negative 1, we have the trend change from increasing to decreasing. So x equals negative 1 will be a relative maximum. X equals negative 1 did come from the numerator of the first derivative. So it will be a normal relative maximum. It has an x-coordinate of negative 1 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. Y equals f of negative 1, which is negative 1 squared plus 3 times negative 1 divided by negative 1 minus 1. Negative 1 squared is positive 1. 3 times negative 1 is negative 3. Negative 1 minus 1 is a negative 2. 1 minus 3 is a negative 2. Over a negative 2. Negative over negative is positive. 2 over 2 is a 1. We have a corresponding y-coordinate of positive 1. X equals 1 is not a critical number. It's a vertical asymptote. Right at the critical number of x equals positive 3, we have the trend change from decreasing to increasing, so x equals positive 3 will be a relative minimum. X equals positive 3 also came from the numerator, so it will be a normal relative minimum. Has an x-coordinate of positive 3 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function, so y equals f of 3, which is 3 squared plus 3 times 3 over 3 minus 1. 3 squared is 9, plus 3 times 3 is also 9 over 3 minus 1, which is a 2. 9 plus 9 is 18 over 2, and 18 divided by 2 is a 9. So we have a corresponding y-coordinate of 9. For part I, we want to determine the intervals of concavity and any inflection points. All of this involves the second derivative, f double prime of x. We'll take it from the first derivative, but we do not want to use the fully factored version. And it will take a little bit of room for this. It can be worked out on the other page. F double prime of x equals. The best version of the first derivative to use to take the second derivative will be the version where all of the terms have been combined together, but it has not yet been factored. That'll be this version here. It is a quotient of two expressions of x, so a quotient rule will again be needed. The derivative of the numerator, which is 2x minus 2, times the denominator left alone, x minus 1 squared, minus the numerator left alone, x squared minus 2x minus 3, times the derivative of the denominator, which is a power rule. Bring the power down, leave the inside alone, subtract 1 from it, it'll be to the first power, and then multiply by the derivative of the inside. And the entire thing will be over the denominator squared. In the numerator, we'll leave the first term alone. For the second term, we can multiply all of the constants. Everything's multiplied, and the order can be rearranged. We have a negative implied 1 times a 2 times a 1. Negative 1 times 2 is negative 2 times 1 will still be a negative 2. We have an x squared minus 2x minus 3, and we have an x minus 1. And all of this is over x minus 1 squared and then squared again, in which case we multiply the exponents. 2 times 2 is a 4. As a rule of thumb, the power in the denominator of each successive derivative should be 1 higher. If we compare the second derivative denominator to the first derivative denominator, it appears to have increased by 2. But that's because in the numerator we have a factor of x minus 1 in each term that can factor out and cancel it back down. We will want to do this. We want to fully factor the second derivative. In the numerator, it has a common factor of a power of x minus 1. We can factor out the lower of the two powers. We have a power of a 2 and a power of a 1. We can factor out the lower, which is the power of 1. Factoring is division, and division is subtraction of exponents. So by factoring out a power of 1, we will subtract 1 from this power. 2 minus 1 becomes 1. There's what we will have left over. 2x minus 2 times x minus 1. And we'll subtract 1 from the implied first power. If we subtract 1 from that, it will become a 0, and anything to the 0 is a 1. And we have minus 2 times x squared minus 2x minus 3. That is what is left over after factoring. So we are left with 2x minus 2 times x minus 1 minus 2 times x squared minus 2x minus 3. And the entire thing is divided by x minus 1 to the fourth power. Now that we've factored the x minus 1 out, we can cancel the 1 power of x minus 1 in the numerator with one of the powers in the denominator. It'll now be to the power of 3. And if we compare it to the first derivative, we see it is increased by only 1, as it should. So f double prime of x equals, inside the square brackets, we can FOIL out these two expressions, 2x minus 2 times x minus 1. First, 2x times x is 2x squared. Outside, 2x times a negative 1 is a negative 2x. Inside, negative 2 times x is a negative 2x. Last, negative 2 times a negative 1 is a positive 2. And we can distribute a negative 2 into this, which will give a negative 2x squared, a positive 4x, and a positive 6. All this is over x minus 1 cubed. We want to combine like terms together in the numerator. There is a positive 2x squared and a negative 2x squared that will fully cancel. There is a negative 2x, another negative 2x, which is negative 4x, add to the 4x, which will fully cancel. We have a positive 2 and a positive 6. Those will add together to become positive 8. And we will leave the denominator as is, because it is already factored into x minus 1 times itself 3 times. There's the version of the second derivative we're going to want. It came out to 8 divided by x minus 1 quantity cubed. We have the second derivative written as a single fraction. All powers are positive, and it is fully factored. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. The numerator has no x's, and 8 cannot equal 0, so we have no candidate numbers coming from the numerator. In the denominator, the x minus 1 factor tells us that x equals positive 1. We'll now check to see if this is in the domain. The domain is all real numbers except positive 1. Well, it's not in the domain then. And it also is not a candidate number, so we have no candidate numbers here. We can draw a domain line, a line representing the domain. It is all real numbers. So it begins at negative infinity, has no left end, and ends at positive infinity and has no right end, except for x equals positive 1, which is not included because it is a vertical asymptote. So the domain is already split into 2 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to positive 1, we can pick 0. And the next interval, positive 1 to positive infinity, we can pick positive 10. We can test the concavity by plugging the test values in the second derivative. We only care whether it's positive or negative here, so the best place to plug in is the fully factored version. That is this one here. The denominator is raised to an odd power here, so it can be positive or negative. But the numerator is positive and will not affect whether the second derivative is positive or negative. Only the denominator matters here. Plugging in, test value is 0. 0 minus 1 is negative. Negative cubed is negative. We have a negative second derivative. This corresponds to concave down. Plugging the test value of 10 into the portion of the second derivative that matters, 10 minus 1 is positive. Positive cubed is positive. We have a positive second derivative, and this corresponds to concave up. We had no candidate numbers here. X equals 1 is a vertical asymptote, and so there are no inflection points at all. We can now draw the graph. There is a vertical axis and a horizontal axis. We have the domain is all real numbers except for positive 1, and that's because we found positive 1 to be a vertical asymptote. So we can sketch that on here as a vertical dashed line. label it right at x equals positive 1. We had no symmetry. We have a y-intercept of the origin. We can label that. We had two x-intercepts, the origin being one of them. If we find the origin to be the y-intercept, one of the x-intercepts at the very least will also be the origin. It's crossing both axes. We also have -3, 0 as the other x-intercept. We can label that one as well. We have a vertical asymptote at x equals positive 1 that we've indicated already. On the left side, the graph should be approaching -infinity, and that means that it will be headed down here. So we'll indicate that that is the case. And on the right side, it is approaching to positive infinity. So the graph should be up here. We'll indicate that that is the case. We have no holes in the graph. We have a slant asymptote of y equals x plus 4. Now, y equals x plus 4, if x is -4, y is 0, so that means it will cross the x-axis over here. And it's going to be a slant asymptote, so we want to make sure it's slanted. It has a slope of 1. When x is 0, y will be 4, so it crosses here at 4, and it crosses here at -4 for x, since y is going to be 0 then. Right at the point of -1, 1, we have a relative maximum. -1, 1 will be in here somewhere. We can label that -1, 1. It's going to have a relative maximum type of shape, so it'll look something like so. And right at the point of 3, 9, we will have a relative minimum that will be up here. We can label that as 3, 9. It's above the slant asymptote y equals x plus 4, because if x is a 3, 3 plus 4 is 7, so it's going to certainly sit above it. And it will have a relative minimum type shape to it. And we found that there are no inflection points. So to the left of the x equals positive 1 vertical asymptote, we should have it remaining concave down the entire time. It's increasing, and then it's decreasing on each side of the x equals -1 critical number, which we found to be a relative maximum. It stays concave down, and it will have an increase and decrease. And it's got to follow this slant asymptote as x approaches -infinity. It should approach it. So we'll have it shaped like so. And it has to remain concave down the entire time. It's now going to be decreasing, and it's supposed to approach the vertical asymptote, so it'll look like so. To the right of the vertical asymptote, x equals +1, we have it remaining concave up, and it will decrease to left of the critical number x equals 3, and then increase to the right of the critical number x equals 3, making x equals 3 be the relative minimum. So it should remain concave up the entire time. So it will be here, and like so, approaching again the slant asymptote of y equals x plus 4 as x goes to +infinity. It has a domain that is all real numbers except +1. And that's a vertical asymptote, and it is approaching the slant asymptote on the left and right, so all properties are being followed here. So this will be the graph of f of x.